Welcome my dear learners for this course on finite element analysis. In our module 4 we were discussing about analysis of heat transfer problems and fluid flow problems. So far we have discussed and concluded our discussion on analysis of heat transfer problems. We have conducted the analysis of heat transfer through composite wall and also through extended surfaces, that is fins. So from today's class we are heading to discuss the analysis of fluid flow through porous medium. In today's lecture, let us derive the differential equation for one-dimension fluid flow through porous medium and also the finite element formulation for analysis of fluid flow through porous medium. Now, to derive the differential equation in one dimension for fluid flow through porous medium, let us consider the control volume. So, if we consider the control volume of a porous medium, let Vx be the velocity of the working fluid entering the control volume and Vx plus dx be the velocity of the working fluid leaving the control volume. And also considering Q amount of internal volume flow rate, let the cross-sectional area of this control volume be A, whereas the length can be taken as dx. That is, let Vx be the velocity of the working fluid entering the control volume, Vx plus dx be the velocity of working fluid leaving the control volume, rho be the density of the fluid, dx be the length of the control volume, A is the cross-sectional area of the control volume and Q be the internal volume flow rate. Now, for this control volume, if I apply law of conservation of mass, from law of conservation of mass of the working fluid entering the control volume plus mass generated inside the control volume is equal to mass of the fluid moving out of the control volume. By knowing the velocity of the working fluid entering the control volume, I can extract the mass of the working fluid entering the control volume by using the equation velocity x into density of the working fluid times the cross-sectional area multiplied with time duration. So this will give us the mass entering the control volume plus there is a Q amount of internal volume flow rate. So therefore mass generated inside the control volume will be Q times rho into dt. This will be equal to mass of the working fluid moving out of the control volume, which is given by velocity Vx plus dx times the density times the area into dt. Let this be equation number 1. Now, the velocity of the working fluid entering the porous medium can be analyzed by using Darcy's law for fluid flow in porous medium. So now, from Darcy's law for fluid flow in porous medium, which states that velocity of the working fluid in the porous medium is directly proportional to the hydraulic gradient d phi by dx. And to equate this, we have proportionality constant as permeability in fluid flow, that is Vx will be equal to minus kx d phi by dx. So this is the equation from Darcy's law of fluid flow through porous medium. This negative sign indicates that flow takes place from higher gradient to lower gradient, whereas Kx is the permeability of the porous medium and d phi by dx is hydraulic gradient. Where now using this Darcy equation for fluid flow through porous medium in the conservation law of mass, I will get minus kx d phi by dx density times the area into dt plus q rho dt is equal to Vx plus dx can be written as Vx plus dVx by dx into dx whole multiplied by density times the area into time. Density times the area into time. So simplifying this equation, we will end up with minus kx times the hydraulic gradient into density into area into time plus internal volume flow rate times the density into time is equal to, we know the value of Vx from Darcy's law, we have minus kx d phi by dx into rho a dt. Substituting for this one, we have again minus d by dx of using Darcy law for flow through porous medium. Once again, we have Vx as kx d phi by dx rho a dt into dx. Now cancelling off these two terms, rearranging the terms, I will end up with d by dx permeability times d phi by dx rho a dt into dx plus q rho dt is equal to 0. So now throughout divide this equation by rho a dt dx. I will get d by dx of kx d phi by dx plus q by a dx is equal to 0. So q by a dx can be considered as internal volume flow rate per unit volume. I can write the final differential equation as d by dx of permeability times the hydraulic gradient plus the internal volume flow rate per unit volume is equal to 0. This is the differential equation for one dimension fluid flow through porous medium, where q prime is nothing but internal volume flow rate per unit volume, whereas the unit of internal volume flow rate is meter cube per second, whereas the internal volume flow rate per unit volume is given by per second. So this completes the expression for differential equation in one dimension for flow through porous medium. Now let us move on and discuss the finite element formulation for fluid flow through porous medium. Under finite element formulation, the first important thing to be noted down is shape function. As you all know, for structural analysis, the nodal variable is displacement. For heat transfer analysis, the nodal variable is temperature, whereas for fluid flow problems, the nodal variable is velocity potential. So therefore, for deriving the shape function for fluid flow analysis through porous medium, I should assume the interpolation function or the approximate function for the field variable, which is nothing but velocity potential. Let us assume the simplex element, that is two noded element for formulation. If I assume the two noded simplex element for formulation, the interpolation function or approximate function for the field variable, which is nothing but velocity potential, can be written as P is equal to A0 plus A1x. As we all know, this is the simplest polynomial equation for simplex element which satisfies the convergency criteria, whereas P is nothing but velocity potential, which is the field variable for fluid flow, which is analogous to displacement in structural analysis and temperature in thermal analysis. Now consider an element in Cartesian coordinate. Let the distance of node number 1 be x1 and the distance of any point on this element be x and the distance of node number 2 be x2, whereas LE be the length of the element. At node number 1 we have the velocity potential as P1. At node number 2 we have the velocity potential as P2. Now substituting the boundary conditions at node number 1 and node number 2 in equation 1, we have the boundary conditions as at node 1 the value of x is x1 and the value of velocity potential is P1. That is, velocity potential is equal to P1 and x is equal to x1. So substituting this in equation 1, I'll get the velocity potential at node number 1 P1 is equal to A0 plus A1 x1. Similarly, the boundary conditions at node 2 are at node 2 the velocity potential P is P2 and distance x is x2. So if I substitute this condition in equation 1, I'll end up with the velocity potential at node 2 as P2 is equal to A0 plus A1 x2. Consider this as equation number 2 and this as equation number 3. Now find the values of constants A0 and A1. If I want to find the constants A0 and A1 using these two equations, we have two unknowns. Now to find constants A0 and A1, let us use equation 3 minus equation 2, which yields us P2 minus P1 is equal to A1 times x2 minus x1. So therefore the constant A1 is equal to P2 minus P1 divided by x2 minus x1. The value of x2 minus x1 is nothing but length of the element. Now to find the value of A0, let us use equation 2. From equation 2 I can write A0 as P1 minus A1 x1. So I know the value of A1, substitute A1 and simplify, find the value of A0. If I do that, I'll get A0 is equal to P1 minus A1. So A1 is P2 minus P1 multiplied by x1 divided by length of the element. In order to simplify, express the length of the element as x2 minus x1. Now taking the LCM and simplifying which, I will get A0 is equal to P1 x2 minus P1 x1 minus P2 x1 plus P1 x1 throughout divided by x2 minus x1. Cancelling off these two terms, you will get A0 as P1 x2 minus P2 x1 divided by length of the element. So thereby we have calculated the constant in this polynomial equation A0 and A1. Now substituting A0 and A1 in equation 1 and simplifying, I get the velocity potential P at any point in the element is equal to P1 x2 minus P2 x1 divided by length of the element plus A1x, that is P2x minus P1x divided by length of the element. Now further simplifying, I'll get the velocity potential at any point in the element is equal to P1 of x2 minus x by length of the element plus P2 of x minus x1 by length of the element. So this is of the form u is equal to n1 u1 plus n2 u2 for analysis of one dimension bars. Similarly here P is equal to N1 P1 plus N2 P2, where N1 and N2 are shape functions. So this is of the form P is equal to N1 P1 plus N2 P2. That is the global potential is equal to shape function into nodal potential, where Q is equal to nodal potentials, that is P1 and P2, which is a column matrix, and N is equal to N1 and N2, which is a row matrix, which is given by N1 is x2 minus x by length of the element, and N2 is x minus x1 by length of the element. Now if I plot the variation of the shape function, we have N1 is equal to x2 minus x by length of the element. Let us consider the element. Now at node number 1, the value of x is x1. So substituting x1 here, x2 minus x1 is LE. LE by LE will gives us the value as n1 as unity. So if I plot, I'll get 1 at node 1. N1 is equal to 1. At node 2, the value of x is x2. x2 minus x2 will become 0. So the value of shape function n1 is 0 at node 2. The variation is linear. Coming for variation of shape function n2, n2 is given by x minus x1 by length of the element. So consider the element of length LE with node numbers 1 and 2. At node number 1, the value of x is x1. If I substitute x1, x1 minus x1 will become 0. So therefore n2 is 0 at node 1. Now the value of x at node 2 is x2. So if I substitute x2, x2 minus x1 is length of the element. So therefore length of the element divided by length of the element will gives us n2 as unity. So therefore n2 is equal to 1 at node 2 and 0 at node 1. The variation is linear. So this completes the expression for shape function for analysis of fluid flow through porous medium and the variation of shape functions. And also if you verify the properties of shape function, the first property, sum of shape function at any node is unity. At node 1, if you verify, n1 is 1, n2 is 0. So therefore the sum of shape function n1 plus n2 is equal to 1 at node 1. Similarly at node 2, n1 is 0, n2 is equal to 1 at node 2. So therefore sum of shape functions at node 2 is also equal to unity. The first property is satisfied. Coming for the second property of shape function, the value of shape function is unity at its own node and 0 at any other node. That is also satisfied. n1 is 1 at node 1, at any other nodes its value is 0. Similarly for n2, its value is unity at its own node and 0 at any other node. Now let us derive the element stiffness matrix, which is very important to analyze the problems. Coming for the second important expression in finite element formulation, that is element stiffness matrix. The general expression for element stiffness matrix in finite element analysis is given by K of any element is equal to volume integral of B transpose, that is strain displacement matrix transpose, into material property matrix into strain displacement matrix times the volume. So this is general expression for element stiffness matrix in finite element analysis, where B is the strain displacement matrix, D is the material property matrix. So D for structural analysis is Young's modulus, whereas for analysis of torsions of shaft, the material property is modulus of rigidity, whereas for heat transfer problems, the material property matrix D is nothing but thermal conductivity, whereas for analysis of fluid flow problems, the material property matrix is nothing but permeability. So now the strain displacement matrix is nothing but matrix containing the derivative of shape function, that is where B is strain displacement matrix, which is given by matrix B is equal to derivative of shape function, that is nothing but d by dx of n1 N2. Just now we have derived the shape function, so therefore B matrix will be d by dx of x2 minus x by Le and x minus x1 by Le. Now differentiating the shape function N1 and N2, I will get the material property matrix B as differentiation of shape function N1 is minus 1 by Le and shape function N2 is plus 1 by length of the element. So this is the expression for strain displacement matrix. The strain displacement matrix is minus 1 by length of the element and plus 1 by length of the element. Whereas the material property matrix D, since this is a one-dimensional analysis, the material property matrix for fluid flow problems is equal to K, which is nothing but permeability. We know B matrix, also D matrix. Substitute this equation and solving, I will get the element stiffness matrix K of any element is equal to integral over the length B transpose, that is minus 1 by Le plus 1 by Le into material property matrix is permeability times the B matrix, that is minus 1 by Le plus 1 by Le. We have changed the volume integral to integral over the length, that is A into dx. Taking constants outside, I will end up with thermal conductivity is equal to area times the permeability K into, so these two matrices are constant, so therefore I cannot integrate dx, so I will get the product of minus 1 by Le plus 1 by Le into minus 1 by Le and 1 by Le times the integration over the length dx. So if I simplify, I will get area times permeability minus 1 by Le into plus 1 by Le is 1 by Le square minus 1 by Le square minus 1 by Le square and plus 1 by Le square. So integral of dx and substituting the limit, I will get Le. So simplifying which and taking Le common, the element stiffness matrix for analysis of fluid flow through porous medium is given by A K by Le 1 minus 1 minus 1 1, where A is the cross sectional area, K is the permeability, L is the length. This completes the derivation for element stiffness matrix for fluid flow problems in porous medium. Coming for the equilibrium equation, the equilibrium equation remains same. The global stiffness matrix times the nodal variables. The nodal variables are velocity potentials and F is the global load vector. So Q is the nodal variables which consisting of velocity potentials of the element. Now coming for the load vector, we have load vector due to flux. If fluid is entering the element, then the load vector due to flux velocity is given by cross sectional area times V and 0. If fluid is leaving the element, then load vector due to flux, that is velocity, is equal to cross sectional area times 0 minus V. This is analogous to heat flux in analysis of heat transfer problems. Fluid entering the element is taken as positive, fluid leaving the element is taken as negative, where V is the velocity of the fluid. Now coming for internal volume flow rate, the load vector due to internal volume flow rate is given by Q bar area times length of the element divided by 2 1 1, where Q bar is volume flow rate per unit volume. Its unit is per second. So for any problems in fluid flow analysis in a porous medium, one should check for these two load vectors. With this knowledge, we can solve problems on analysis of fluid flow through porous medium. The important points to be remembered are the element stiffness matrix, which is given by cross sectional area times the permeability divided by length 1 minus 1 minus 1 1. the nodal variables which are nothing but velocity potentials and the load vectors. That's all from this lecture. Thank you.